Ladies and gentlemen, introducing the Ficken Colton.
There are steps to follow when optimizing. You rather want to know whether you're going to do a max or min would be the first step. When optimizing, you usually get two variable equations, such as like if you had an equation like area, which would be base times height. You need to get this equation either into one variable form, either b or h, for instance.
Say what?
Now you gotta write the derivative of the equation in its two variable form. The next step is to set the derivative to 0 and find if it's a maximum or minimum using a second derivative test. Depending on what the question asks, you might have to plug the variable back into the original equation.
We're actually now going to try our 6-step formula for a problem here and show you that it actually does work, and will lead you to an answer. The problem is find the maximum area of a rectangle that has two vertices on the x-axis and two vertices on the graph y equals x squared minus 8. So we know that we were trying to find a max, and from that you need to find the area. We're finding an area of a rectangle, and so since a parabola, it's not shifted either way on the y or the x-axis. This right here is going to be x, and this right here is going to be x. So one side of the area, which area equals, we'll just go x times h times the height here. That'd be 2x times h. And then we know that the h is going to be the y distance, or the y, of x squared minus 8. So you have a equals 2x times x squared minus 8. And that's your formula right there. So then you distribute through. So an area equals that, and then you need to find its derivative, which a prime would be. (6x squared minus 16), and then you set that equal to 0. So you set a prime to 0, like I said. And so you set that to 0, you can factor out a 2, 3x squared minus 8, and then you know that when this equals 0 is when your equation is going to equal 0, so you just don't even worry about the 2. So you have 3x squared minus 8 equals 0. Add 8 over, divide by 3x squared equals 8/3, and then you need to find the square root of that. So then x equals plus or minus the square root of 8/3. Now that we have our critical points, which is the square root of 8/3 plus or minus, we plug those into the second derivative. We're doing the second derivative test. You plug those in the second derivative of the area, which would be a prime prime. And that's 12x. And then when you plug these values in, which you plug in positive square root of 8/3, you're going to get a positive answer, and vice versa for the negative. And then we know we're trying to maximize this, so we want the negative, so we need the negative square root of 8/3. Alright, now that we have our max, we can plug it back into the original area equation, which we had for one variable. And then you plug in negative square root of 8/3. Plugging that into our calculator, we found that Our answer is 17, or is approximately 17.4186 units squared.
For the second problem, we have a open box. And we're supposed to find the maximum dimensions, the dimensions that give it the maximum volume. The whole box uses an area of 120 centimeters squared cardboard. Now that we have a equation for height, we can plug this into the volume equation. Volume is going to be the length squared times the height. And then plugging this in for h, we get L squared times 120. So our volume equation comes to 1 to the 4th minus 420 L squared over negative 4L. Now we need to find the derivative of this. Our volume equation simplifies to L cubed minus 120 L over negative 4. Then we got to find the derivative of this, which is going to be negative 3/4 length squared minus plus 30. And then we need to find the zeros of this equation. Which comes to 30 equals negative 3 positive 3 length squared 4. Length squared equals 40. Our length equals the square root of 40, plus or minus. Now we got to move on to the second derivative test. For the second derivative test, we need to find our second derivative, which is going to be negative 6 length over 4. And we're going to plug in our first derivative zeros. Negative square root of 40 is going to give us a positive number, concave up parabola, and square root of 40 is going to give us a negative number, which is going to be a concave down parabola, which is where our maximum is going to occur. Now that we know our maximum length is at the square root of 40, we'll plug that back into our height equation found from earlier, and we get approximately 3.16, and that's optimization.